Hi, my name is Dr. Anthony Rizzi. I want to introduce you to a new textbook, Physics for Realists. It's a common sense approach to physics that teaches students how to start with the things they know right in front of them and move to deep into, as far as you'd like to take them, into the equations. Or if you'd like, just into a sort of proportionality approach. Or you can stop with the fundamental common sense principles, because the unique thing about this book is the principles are accessible to everyone. It is a calculus-based book, so to use the entire book, you'd have to have students that have had some calculus. But if the teacher digests it, the main principles, the central principles of Newtonian physics are now available for the first time in a form that can be taught to even very young children. And we've done that. We've taught to very young children, and they actually remember these principles. And students remember things like what momentum is and the nature of Newton's first law the first time, and of course get better with practice. So I want to start by giving you some kind of idea of this new approach, because as all things new, you'll be wondering, what is it? And the first thing I want to start with is measurement, because we teach measurement, like many of the concepts of Newtonian physics, as a sort of apprenticeship in using. So in other words, it's a teaching of how to, and really it shouldn't be. As you know, physics is about things and wanting to tell us something about what they are and what they do. So the very simple concept of relation, every child knows, and we start with that in terms of measurement. We say, what is measurement? And normally we would say, in our sort of apprenticeship mode, it's that which does that which a measurement instrument gives. And of course that doesn't help the student's mind grasp conceptually what we mean. So we go to this idea of relation. So what a measurement is a relation. It's a relation between two things. So for example, this metered stick has a length to it. And that length is not a number. It's just a certain extension, or length, if you will. I also, when I'm standing up, have a certain extension. I have one now, but when I'm standing up, I have a certain one. And if I take two of these meters side by side and stand them up, two of those will equal about one of me. And so the comparison between the length of me, which is not a number either, and the length of this gives me a number too. So in that comparison, I get a number that captures something essential about me that I can then use in my equations. And that way I show the student how I start from this common sense idea of a relation and get a number that then I can use in my equations. Another example is even more profound, is the idea of impedance. And it starts with another everyday thing that every child, small child, knows, and that is, if I take an object and throw it, it moves. And the question I like to ask the student, is very simple. We're starting very simple with things that they do all the time and have done since very small. Why does it move? Now, the first thing any child will tell you is that it moves because you moved it. But you've got to bring their attention to the fact that the thing keeps moving. After they let it go, it keeps moving. It keeps going even after they've let it go. And so that brings them to the causal question, is what makes it keep moving? And that's where we bring the answer to them. It's impetus. We have given the ball a quality, a property called impetus, and we tell them the nature of this property. The nature of this property is to move the ball uniformly in a straight line. And it will keep doing that because the impetus, that's the nature of that impetus, that quality we've given the body, to keep moving it uniformly, unless something changes that impetus. And that something, of course, that changes the impetus is the force. So then we move very quickly to smooth surface, because the smooth surface will take away this falling ball that we have to deal with. In other words, it brings in gravity, which is more of a complexity that maybe we want to address right away. So we just move to here and we say, look, I gave that ball some impetus. And notice how that impetus keeps the ball moving. And this is a low enough friction case that it looks that the student can see that it looks as if it's just continuing to move without any diminishing of its speed. And we can tell them, see, that's the impetus. The impetus keeps moving it. And then you say, well, it does, you notice, slow down. You could ask the student, what would happen if I just let it keep going? Would it go on forever? And they would know intuitively, again, from their common experience, that it would not keep moving. And then you'd get to ask them, what is it that stopped it, finally? And then you bring out to them, well, what's in contact with it? Well, for one, the desk. And then you could bring up the idea of friction and make it come home by taking it, say, a roll of masking tape and pushing it. And the masking tape stops very quickly. It moves for a bit, but it stops. And that's, we can tell them, because the force, the property of the desk, is able to deactivate the impetus very quickly. It's a larger force. The force is the rate of change of the impetus, the intensity of the impetus, the rate of change of the intensity of the impetus. So it's a much higher friction. The friction here is much lower, thereby introducing very quickly the concept of force and impetus, and showing their interrelation, and showing that force is a property of a body. That also handles this problem we often have with students of abstracting the force and not connecting it with the body. Well, once they understand the force is a property of a body, then they're not going to do that. This happens over and over again in the teaching of physics, that we leave out the very simple nature of things that students, their minds would want to ask first, that then come back and bite them in solving problems or even thinking about how to solve a problem. So this is just a tip of the iceberg of giving you the approach of our new text. But I wanted to give you that tip because it's only in seeing that you can see how it's going to open up the world for your students. One last thing that I wanted to tell you of the many new things that's in the book is our unifying practical theme. You know, I like to tell people that the sci-fi-ness of youth that they're introduced to, if I can say it this way, the Star Trek-ish sort of theme really ignites the imagination of kids, and it is behind it's the reason behind so many students become interested in science. And we have a real, not sci-fi, but sci-real, you might say, because we're really planning to go to Mars by 2030. So this can ignite the imagination of the student, and we do, every time they get a new concept, they get to apply it to their manned trip to Mars, so that by chapter 9, after they've gone through all Newtonian physics, they now have the tools, surprising to them, and maybe to other people as well, that they now can plan their whole trip to Mars and work out all kinds of problems that they thought they couldn't. This takes the student from the abstract ideas, forcing them to make decisions on what approximations to make, what things to include, what things not to include, that we've been doing throughout the book, but this gets a chance to really make them focus because they've got all this information and this simple task that is go to Mars. Simple, exciting task. And in that, we bring in all kinds of other issues as well, showing that physics is about the everyday world and is an exciting, deep, profound, wondrous thing about the very world around them, but also about the world of the heavens. And in fact, the last thing I want to say about this is that Mars, many people don't realize, is central to the way Newtonian physics even came about. Because Tycho Brahe, that great experimentalist that did those fantastic measurements of the visible planets, asked Kepler to study Mars. And that was really important because Mars, only Mars has this large eccentricity of the visible planets anyway. And if he had assigned a different visible planet, it would have not, even as good as his measurements were, it would not have been enough of a eccentricity for Kepler to see the ellipticity of the orbits of the planets, and therefore would have not came up with his great Kepler's laws that led immediately to Newtonian physics and Newton's insights into the physics that this whole textbook is about. And of course, who knows what would have happened to Newtonian physics, whether it probably would have not been discovered then, at least at that point. So it's a profound way of bringing in history as well. And of course, the biggest piece of history is that Newtonian physics was verified by the visible planets. That's why people believe Newtonian physics, and again, that's why Newton was able to think of the ideas and see so profoundly into the nature of physical beings at this level. The last thing I want to tell you is that there's a chapter on special relativity at the end. All of Newtonian physics, including things on temperature and pressure, and at the end, a chapter on special relativity for those who would like to introduce their students using this same intuitive approach. So please check out this new book. Buy yourself a copy. Get some for your students. I think you will find it, as we have in our teaching and the professors that have used it, an invaluable way of teaching physics and getting a broader cross-section of people interested. And as I say, once you get the principles, it can be used at any level, even for young children. But the book is a top level. It has a solutions manual with it, and has the ability to cover this range of even the most advanced problems. So check out the book at the Institute for Advanced Physics, and you can buy a copy maybe online or at one of our conferences that we're having around the country. Thank you.